Okay, yaar. Okay. So hi everyone. So good afternoon all. Okay. So let me know if audio and video everything clear. So good afternoon all. Right. So if audio and video is not clear, please comment in chat box here. Okay. So I hope audio and video everything is clear. I hope so. Right. Okay. Okay. So we are dealing with the subject electromagnetics, and in electromagnetics we have started the topic magnetostatics. There we have completed a Lorentz force equation, and also we completed Biot and Savart's law. So then we have started with Ampere's law. So we have seen the applications of what? The applications of Ampere's law. Yes or no? Okay. So with the help of Ampere's law, how to determine the B field, how to determine the B field due to a current carrying wire, of infinite length. How to determine the B field inside the current carrying wire, and how to determine the B field outside the current carrying wire. So all these things we have seen, right? Okay. And in the previous session we have seen that how to determine the B field inside what? Inside the cavity. Yes or no? Okay. So this is the cross section of the cylindrical wire. So we have considered the radius of this bigger sphere as A, and the radius of this cavity or hole is nothing but B, and we try to determine the magnetic field at some point P inside the cavity. Understood? Okay. So what we have done here, we have splitted this into two current distributions. So one is of radius what? One is of radius A, and another one we have considered as radius B, right? So so we have splitted this into two cylindrical wires, right? So one is carrying a current density of Z, right? So which is in AZ cap direction, and we have assumed this is carrying a current density of Z in opposite direction, that is in negative Z direction. Understood? Okay. Okay. Here. So we have already done all these things here. So what is the expression we got here inside the cavity? What is the expression we got? So B field inside the cavity we got as what here? We got mu into what? Mu into Z bar cross D bar divided by what? Divided by 2. So this is the expression for B field we got. Yes or no? Okay. Okay. Yeah. So here this D is nothing but what here? D is nothing but the distance between the centers of the two cylindrical wires. Okay, the distance between the centers of the two cylindrical wires. So that is nothing but what? That is nothing but D. So we have seen that inside the cavity, the magnetic field inside the cavity, the magnetic field is equal to what? Mu by 2 into Z bar cross what? Z bar cross D bar, where D is the distance between the centers of the two cylindrical wires. So that means B field inside the cavity is going to depend upon what? It is going to depend upon the distance between the centers of the two cylindrical wires. It doesn't depend upon this radius A, and it doesn't depend upon this radius B. It depends only upon what? It depends only upon the distance between the centers of the two spheres, and whatever the point you can take inside the cavity, or whatever the point you can take inside the cavity, you are going to get what? You are going to get the same expression. Understood? So that means inside the cavity, the magnetic field is what? The magnetic field is uniform. Understood? Okay. So at each and every point inside the cavity, you are going to get the same value of what? Same value of magnetic field. So that means magnetic field inside the cavity is what? Inside the cavity is uniform. Okay. So that's what we have concluded. And also we have seen one special case here. So that is if you consider this cavity, okay, if you consider this cavity exactly at this center here, So let us say this is radius B and this is radius A. Okay. So for this one, in this case, what happens here? The distance between the centers of the two cylindrical wires is equal to what? Is equal to 0. Why? The center of this bigger cylindrical wire and the center of this cylindrical wire, both are what? Both are coinciding. So in this case, the distance between the centers of the two cylindrical wires is equal to 0. So that means in this case D is equal to what? D is equal to 0. So if D is equal to 0, then B field will become what? B field will become equal to 0. So that means inside the cavity at each and every point, what is the value of magnetic field here? The value of magnetic field will become equal to 0. Okay, so all these things we have seen in the previous session itself, right? Okay, yeah. So now okay, so now in this session we will try to determine the B field inside a solenoid of infinite length, right? Okay, so these are all applications of Ampere's law here. With the help of Ampere's law, we are trying to determine what? We are trying to determine the B field, right? Okay, here. So let us consider a solenoid of infinite length. Solenoid of infinite length. Okay, so we try to determine the B field inside the solenoid of infinite length, right? Okay, yeah. So just I am drawing the solenoid here. Okay, so let us consider this as what? This as solenoid of infinite length. So it is extending in this direction. So it is extending in this direction up to infinity. Right? Okay, yeah. So now see here, right? Okay. Okay, so this is the, let us consider this is the solenoid of infinite length. This is the solenoid of infinite length, right? Okay, so it is extending in this direction up to infinity. So let us consider this is the axis of what? Let us consider this is the axis of solenoid. Let us assume this is the axis of solenoid, right? So this axis I am considering as Z axis here. This axis I am considering as Z axis. Okay, yeah. So now let us consider the current is flowing through the solenoid. And we want to determine the B field inside the solenoid. Okay, so now here I am considering the current is flowing through this solenoid in anti-clockwise direction. I am considering like this here. Okay, so it is flowing like this. So here it is coming out of the board, and here it is going into the board, and again here it is coming out of the board, and here it is going into the board. Here again coming out of the board. Here it is going into the board. Here it is coming out of the board, and here it is going into the board. So in this manner the current is flowing through the solenoid. Right? Okay, so here it is coming out of the board, and here it is going into the board. Here it is coming out of the board, and here it is going into the board. So out of the board, into the board, out of the board, into the board, right? Okay, so in this manner the current is flowing through the solenoid, right? Okay, okay, yeah. Okay, now see here, so we want to determine the B field inside the solenoid, right? Okay, okay, yeah. See, the same thing here, I will represent in this manner here. The same solenoid I am representing in this manner. Understood? So here I am just representing this currents here. I am representing the currents. So here it is coming out of the board. Yes or no? So here the current is coming out of the board, and here the current is going into the board. Here the current is coming out of the board. Here it is going into the board. Here it is coming out of the board. Here it is going into the board. So coming out of the board, into the board. So coming out of the board and into the board. So coming out of the board and into the board, right? Okay, so in this manner I am representing the same here. I am representing the same thing in this manner. Okay, so just I am representing the current elements, right? Okay, so I am not representing this total diagram here. I am just representing this current elements here. So in this manner I am representing. So you have to assume this as what? This as a solenoid of infinite length, and the current is flowing in this manner. The current is flowing in anti-clockwise direction in this manner. Okay, so the same diagram I am representing in this manner. That's it. Okay, so hope you have understood this one, right? Okay. Right. Okay, okay, yeah. So now see here, okay. So this is the axis here. This is the axis of the solenoid, right? This is the axis of the solenoid. Okay, so this axis we have considered along what? Along z direction. This axis is along z direction, right? Okay, so this is inside the solenoid, this is outside the solenoid, this region is also outside the solenoid. Now see here, here the current elements on this side, are pointing out of the board here. The current elements on this side are pointing out of the board. So if the current is pointing out of the board means on this side, what is the direction of B field here? See, if the current is flowing out of the board means on this side, to the left side, it is going to point in downward direction and it is going to circulate like this. So to the right of this one here, the magnetic field is going to point in upward direction. Yes or no? See, if the current is flowing out of the board, then to the left of this current carrying wire, the B field is going to point in downward direction. To the right of this current carrying wire, the B field is going to point in upward direction. Yes or no? Okay, so due to all these current elements here, on this side, to the left of this current elements, the B field is going to point in downward direction. To the right of this current elements, the B field is going to point in upward direction. Yes or no? Okay, okay. So that's what I am representing here. So due to this current element, to the left of this one, the B field is pointing in which direction? The B field is pointing in downward direction. Understood? And to the right of this one here, the B field is going to point in which direction? Due to this current elements. Forget about this here. I am considering only this current elements. So due to this current elements, to the right of this one, the B field is going to point in upward direction. So that means here it is going to point in upward direction, right, to the right of this one. And here outside the solenoid, due to this current element here, the B field is going to point in which direction? It is going to point in upward direction. Right? Okay. Okay. Yeah. See, if the current element is pointing out of the board means to the left of this current element, B field is going to point in downward direction. To the right of this current element, the B field is going to point in upward direction. So that's what I have represented, right? Okay. Okay. Yeah. So next, Next, consider this current elements here. Next, consider this current elements. Here, this current elements are pointing into what? Into the board. These current elements are pointing into the board. So, if they are pointing into the board, then what is the direction of B field? To the right of this current elements here, to the right of this current elements, it is going to point in which direction? It is going to point in downward direction. To the left of this current elements, it is going to point in which direction? Upward direction. Yes or no? Okay, so I have explained all these things while dealing with Lorentz force equation and Byte and Sever's law. So there I have explained how to determine the direction of B field, all those things, right? Okay. Okay, here just we are applying right hand rule, that's it. Okay, so if the current is pointing into the board, means to the right of this current element, the B field is going to point in downward direction. To the left of this current element, the B field is going to point in upward direction. Okay, so due to this current elements, okay, so to the left of this one, the B field is going to point in which direction? Upward direction. So this is the B field due to this current elements, and this is the B field due to what? Due to this current elements. Okay, next, inside the solenoid here, inside the solenoid, it is to the left of what? To the left of this current elements. So inside the solenoid, it is going to point in which direction? It is going to point upward direction. Yes or no? Okay, so due to this current elements, the B field is going to point in which direction? The B field is going to point in upward direction. And to the right of this one, the B field is going to point in which direction? It is going to point in downward direction. Understood? Okay, so here the B field due to this one is pointing in upward direction, due to this one the B field is pointing in downward direction. Okay, so this is what we got here, this is what we got. So from this, what we have observed here, if you observe outside the solenoid here, due to this current elements, the B field is pointing in downward direction. Due to this current elements, the B field is pointing in upward direction. So the net magnetic field outside the solenoid is approximately here, will become equal to what? Will become equal to 0. Okay, so what is the assumption I am making here is the distance between this current elements here, this current element and this current element. Okay, so the distance between these current elements and these current elements, I am assuming it as very, very small when compared to what? When compared to length of the solenoid. Understood? Okay, so in that case, the B field produced by these elements and the B field produced by these elements will be almost what? Will be almost becomes same. Okay, so under that condition, I can consider the net magnetic field is approximately equal to what? Approximately equal to 0 outside the solenoid. Understood? Okay, next, to the right of the solenoid here, the same scenario or not? Yes or no? Here the B field due to this current elements is pointing in upward direction. Due to this current elements, the B field is pointing in downward direction. So the net magnetic field outside the solenoid will be approximately equal to what? Will be approximately equal to 0. Now, if you observe inside the solenoid here, due to this current elements, the B field is pointing in upward direction. Due to this current elements also, the B field is pointing in upward direction. So that means you are going to have what? You are going to have net magnetic field inside the solenoid. So the net magnetic field inside the solenoid is not equal to what? Is not equal to 0. Why here? Because due to this one, it is pointing in upward direction. Due to this elements also, it is pointing in upward direction. Understood? Okay, so you are going to have some net magnetic field inside the solenoid. So outside the solenoid, we can make approximately the net magnetic field is equal to what? Is equal to 0. Understood? Whereas inside the solenoid, the net magnetic field is not equal to 0. Understood? We are going to have some magnetic field inside the solenoid. Now we try to determine what is the magnetic field inside the solenoid. Okay, so how we can do that here? So we can do this with the help of what? With the help of Ampere's law. See here how we are going to determine that. See here. See, from Ampere's law, we know that the circulation of B field around any closed loop is equal to what? Is equal to mu times of what? Mu times of current enclosed by that closed loop. Yes or no? So that is nothing but Ampere's law. Yes or no? So the circulation of a B field around any closed loop is equal to what? Is equal to mu times of what? Mu times of current enclosed or current penetrating. Right? Yes. So this is what we have seen. Yes or no? This is nothing but Ampere's law. Right? Okay. Okay. Yeah. So the circulation of magnetic field around any closed loop is equivalent to mu times of what? Mu times of current enclosed by that closed loop. Understood? So now here I am going to form a closed loop, and I will try to determine the circulation of B field around that closed loop. Okay, so how I am going to form the closed loop? See here. So I am going to form the closed loop in this manner here, in this manner. See here. So okay, so this is the closed loop I am forming here. This is the closed loop I am forming. Okay, so this closed loop is also called as what? This closed loop is also called as Amperian loop, or you can simply call closed loop. Okay, so this is the closed loop, or we can name it as Amperian loop, whatever it may be. Okay, okay, yeah. So now we try to determine the circulation of B field. So now we try to determine the circulation of B field, around this closed loop. We try to determine the circulation of B field around this closed loop. Understood? Okay, so what do you mean by circulation of B field around this closed loop here? What you have to do? So along this length here, you have to determine what? You have to determine integral B bar dot what? B bar dot DL bar. Right. Next, along this length, you have to determine integral B bar dot what? B bar dot DL bar. Next, along this length, you have to determine integral B bar dot what? B bar dot DL bar. Next, similarly, along this length, you have to determine what? You have to determine integral B bar dot what? B bar dot DL bar. Understood? Okay, so now if you add up all this here, you are going to get what? You are going to get the circulation of B field around this closed loop. Understood? So I have formed a closed loop here, closed loop or Amperian loop. Now I am trying to determine the circulation of B field, around this closed loop. So how to determine the circulation of B field around this closed loop here? What you have to do? You have to determine integral B bar dot DL over this length plus integral B bar dot DL over this length plus integral B bar dot DL over this length plus integral B bar dot DL over this length. So if you add up all this here, then you are going to get what? You are going to get the circulation of B field, around this closed loop. Okay, so what you are going to get here? See here. Now if you try to find out integral B bar dot DL over this length, what you are going to get here? See the loop here. So this loop here, this line here, okay, so this line is present outside what? Outside the solenoid. Yes or no? So this loop, this part of the loop or this line, okay, so is present outside what? Outside the solenoid. So outside the solenoid, what is the B field here? What is the B field outside the solenoid? Outside the solenoid, B field is equal to 0. So integral B bar dot DL over this length, what you are going to get? You are going to get 0. Why here? Because B field here is equal to what? Is equal to 0. Understood? Since this line is present outside what? Outside the solenoid. Understood? Okay, next. So I am considering this as first section here. Over this first section, integral B bar dot DL bar will be equal to what? Will be equal to 0. Next, if you move from here to here, Okay, so from here to here, from here to here, so this section is present, this section is also present outside what? Outside the solenoid. So if you do integral b bar dot dl over this length here, over this length from here to here, from here to here, what you are going to get? Integral b bar dot dl over this length will also be equal to what? Will also be equal to 0, because this section from here to here is also present outside what? Outside the solenoid. Right. Okay, next this section here, if you observe this section, if you observe this section here, this section, so this section is present what? Is present inside the solenoid. This section is present inside the solenoid. So from here to here, from here to here. Okay, so if you try to determine integral b bar dot dl bar over this section here, over this section, what you are going to get? Tell me what you are going to get. From here to here, what you are going to get? See here, if you observe here, the loop direction here, the loop direction is pointing in this direction. Yes or no? It is pointing in horizontal direction like this. So the loop direction is like this, right? Okay, the loop direction is like this. So inside the solenoid, what is the direction of B field? B field is pointing in upward direction. So that means B field is pointing in upward direction, and the loop direction, that is DL bar direction, is pointing in this direction. Understood? So that means B field and DL bar both are what? Both are perpendicular to one another. So in this case, what you are going to get? Integral B bar dot DL bar is equal to what? Since B bar and DL bar both are what? Both are perpendicular to one another. So what you are going to get? You are going to get integral B bar dot DL bar is also equal to what? Is also equal to 0. See, if these two are perpendicular to one another, means what happens to the dot product? Dot product will become 0. So that means integral b bar dot dl bar over this length will also become equal to 0. Understood? Okay. So from here to here, consider this as second section, and from here to here, consider this as third section. Okay. So over first section it is 0, over second section also it is 0, over third section also it is 0. Right. Okay. Next. Okay, so next, over this fourth section here, over this fourth section, let us name this as fourth section here. So over this fourth section, if you observe, B field is pointing in which direction here? B field is pointing in upward direction, and this DL bar, that means the loop direction, if you consider a small differential length, the DL bar, so this is also pointing in which direction? DL bar is also pointing in upward direction, and B field here inside the solenoid is also pointing in which direction? It is also pointing in upward direction. It is also pointing in upward direction. So that means B bar and DL bar both are pointing in what? Both are pointing in the same direction, and hence integral B bar dot DL bar will get simplified, and you will get simply integral B into what? Integral B into DL. Yes or no here? Okay, so over this length, if you try to determine integral B bar dot DL bar, what you are going to get? You are going to get integral B DL. Why here? Because B field and DL bar, loop direction and B field direction inside the solenoid, both are pointing in what? Over this section. Both are pointing in the same direction. So you are going to get integral B DL. Understood? Okay, next. Next, see here. Next, similarly over this section here, similarly over this section, if you consider this section here, if you consider this section, okay, so over this section, what you are going to get here? Tell me. So over this section, what you are going to get? So over this section, what you are going to get? Integral B bar dot DL bar, what you are going to get? See here, the loop direction, same thing here. The loop direction is in this direction here. Yes or no? DL bar is pointing in this direction, and here inside the solenoid, B field is going to point in which direction? Upward direction. So B bar is pointing in upward direction, and DL bar is pointing in horizontal direction. So the angle between B field and DL bar is equal to what? Is equal to 90 degrees, and hence integral B bar dot DL bar over this length here, over this length will also become what? Will also become equal to what? Will also become equal to 0. Understood? Next, if you consider this section, if you consider this section here, if you consider this section, right? Okay, so let us name this section as 5, right, and this section as 6. So over this section here, over this section, so this section is present, outside the solenoid, and outside the solenoid, just now we have seen that B field is equal to what? B field is equal to 0. So that means you are going to get integral B bar dot dl bar, integral B bar dot dl bar is equal to what? You are going to get 0. Understood? Okay, so that means the circulation of B field around this closed loop, what you are getting here. So in order to get the circulation of B field around this closed loop, what you have to do? You have to add up integral B bar dot dl over this section plus over this section plus over this section plus over this section. So if you add up all this, what you are going to get? Tell me what you are going to get. Here 0, here 0, here 0, here you are getting integral B dl, and here it is 0, and here also it is 0, here also it is 0. Understood? So overall, the circulation of B field here, the circulation of B field around this closed loop, the circulation of B field around this closed loop, what you got here? What you got? Simply integral B into dl. So this is equal to what? This is equal to mu times of what? Mu times of current enclosed by that closed loop. So what is the current enclosed by this closed loop here? So how many current elements this loop is enclosing here? So here 1, 2, 3, 4, 5. Yes or no? Okay. So if suppose in general, let us assume this loop has enclosed, if suppose this Amperian loop or this closed loop is enclosing n current elements here. Okay, if suppose in general it has enclosed, let us assume it is enclosing n current elements, then what you have to write? Mu times of what? Mu times of n into what? N into I. So how many current elements this loop is enclosing? So some n current elements in general. Understood? Okay. Okay. So mu times of what? Mu times of n into I. Mu times of n into I. Understood? Okay. Okay. So now here, if I take B bar outside the integration, then what you are going to get here? Integral dl, which is equal to what? Which is equal to mu into what? Mu into ni, mu into ni. Okay. So integral dl is nothing but what? Integral dl is nothing but the length of this line here, the length of this line. Okay. So let us say the length of this line, let us say the length of this line. Let us say the length of this line is L. Let us say the length of this line is what? Is L. Understood? So then integral dl, I can write it as what here? B into what? B into L. B into L. Right? Okay. So B into L is equal to what? Is equal to mu into n into I. Mu into n into I. Okay. Okay. Phoenix Gaming. Good evening. Good evening. Good evening, Phoenix. Okay. So here B into integral dl is nothing but B into L, which is equal to what? Which is equal to mu into n into I. Right. So therefore B field inside the solenoid, what you are going to get here is equal to mu into n into I divided by what? Divided by L. Now what is the direction of B field here? This is the B field inside the solenoid. What is the B field inside the solenoid? What is the direction? It is pointing in upward direction. Yes or no? That means it is pointing in AZ cap direction. See, it all depends upon how the current is flowing. Here we have assumed that the current is flowing in anti-clockwise direction like this. Okay, and hence the B field is pointing in upward direction. If you considered the current is flowing in clockwise direction here, then in that case the B field is going to point in negative Z direction. It all depends upon how you are choosing the current direction. Understood? So here we have chosen the current direction in anti-clockwise direction, and hence B field is going to point in which direction here? We got the B field is pointing in AZ cap direction. AZ cap direction. So this is the expression for B field inside what? Inside the solenoid. Inside the solenoid. Understood? Okay. Okay. So with the help of Ampere's law, we have easily determined the B field inside what? Inside the solenoid. Inside the solenoid. Okay. So if you observe this expression here, B is equal to mu into n by n I by what? By L. B equal to mu into n into I by L. So this is the B field inside the solenoid of infinite length. Understood? Okay. Okay. So now now if I ask you a question like See here, generally what students will do here is B field is proportional to what? Is proportional to n, is proportional to n. So n represents what here? N represents n number of what? N number of windings. Yes or no? Okay. So here we have assumed that this loop is enclosing what? Is enclosing n current elements. So it is enclosing n current elements means what here? It is enclosing n windings here, n windings of the solenoid. Understood? Okay. So n represents what here? N represents the number of windings. N represents number of windings. Right? N represents number of windings. So generally, if I ask you a question like, if you are having a solenoid, so if you are having a solenoid, right? Okay. So for this solenoid, let us say this is solenoid 1. So for solenoid 1, let us say I have given n is equal to 1000 tons here. N is equal to 1000 tons. Okay. Next, I have considered another solenoid here. So let us say for this solenoid, n is equal to what? N is equal to, let us say this is n1, let us say this is n2. Okay. So n is equal to, let us say 100 tons here. I have considered 100 tons. Okay. Now generally, if I ask students in which case the B field is going to be more. So that means here I am having solenoid 1, it is having 1000 tons, that means 1000 windings, right? And solenoid 2 is having how many tons here? 100 tons. Okay. So if I ask students generally what is the whether the B field is stronger in first case or second case, that means in first solenoid B field is stronger or in second solenoid B field is stronger. So if I ask that question, generally the students will say, since the B field is proportional to n, generally the students will say n for 1000 tons. If the number of tons is more, then they will say B field is more. Okay. So you cannot say that here, directly, because why means it not only depends upon number of tons, it also depends upon what? It also depends upon L. So that means it depends upon what? It depends upon number of tons per unit length. N by L ratio is called as what here? Number of tons per unit length. Understood? So this N by L is called as what? Is called as a number of tons per what? Per unit length. So B field inside the solenoid will not only depends upon n, it depends upon what? It depends upon N by L ratio, that is number of tons per unit length. See, for example, in solenoid 1 case here, if I consider the length of the solenoid as what? As 1000 meters. And in solenoid 2 case, if I consider the length of the solenoid as 1 meter. Okay. So then in which case B field is going to be more? Here if you observe in solenoid 1 case, N1 by L1 ratio is equal to 1. So that means N by L ratio will be 1. Understood? Whereas in solenoid 2, so 100 by what? 100 by 1 is equal to what? Is equal to 100. So N by L ratio will be what? 100. So in which case B field is going to be stronger? So for second solenoid it is going to be stronger. Okay. It not only depends upon the number of tons, it also depends upon what? It also depends upon the number of tons per unit length. It depends upon number of tons per unit length. Understood? So that means if the number of windings are closer here, then the number of tons per unit length is more. In that case, the B field inside the solenoid will be what? Will be more. Understood? So if the windings are loosely packed here, like if the distance between the windings are more. Understood? Okay. So that is if the number of tons per unit length is more, is less. Okay. So then in that case, B field is going to be what? B field is going to be lesser. Okay. So if the windings are closely packed, such that the number of tons per unit length is very, very large, in that case, the B field inside the solenoid will be what? Will be more. Okay. So if you want more B field inside the solenoid, then what you have to do? You have to increase this ratio, that is number of tons per unit length. So what I am saying here is, it not only depends upon the number of tons, it depends upon what? It depends upon number of tons per unit length. Understood? Number of tons per unit length. So that is what is important here, right? Okay. Okay, yeah. So this is the B field. This is the expression for B field inside what? Inside the solenoid. Inside the solenoid. So generally, this N by L ratio, that is number of turns per unit length, in general we can represent with what? We can represent with simply capital N. So capital N represents number of turns per unit length. So in that case, the expression will become very simple. That is, I can write this as mu into what? Mu into N into what? N into I, where N is equal to what? Where N is equal to N by L. Okay, so N represents number of turns per unit length. Okay, okay. So in this manner also we can represent. So just by looking at this expression, okay, don't think that it is don't think that this capital N has number of turns. Capital N is nothing but what? Number of turns per unit length. Number of turns per unit length. Right? Okay. So that is what you have to understand. Right? Okay. So this is the expression for B field inside what? Inside the solenoid. Right? So Abhishek, good evening Abhishek. Good evening. Okay. Okay. So I hope this is crystal clear here. I hope this expression is crystal clear. How we got this expression for B field inside the solenoid. Right? Okay. 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 So if you are having any doubts, you can ask me here. So otherwise, we will go for next topic. Right? Okay. So next. So that is the expression for B field inside the solenoid. Inside the solenoid. Right? Okay. So next we will see one more thing here, that is it will take hardly 10 minutes here. Okay. So Gauss law for B field. Gauss law for B field. So it is very simple here. Gauss law for B field. See here. Here I am considering a magnet here. I am considering a magnet, right? Okay. So this magnet is going to have north pole as well as what? As well as south pole. Now I am enclosing this magnet. With a closed surface, with some closed surface. So this is the closed surface here. Okay. So what I have done here? I have taken the magnet and I have enclosed that magnet with what? With a closed surface. This is not closed loop, this is closed surface. Sorry here. Okay. So this is nothing but what? This is nothing but closed surface. So I am enclosing the magnet. I have enclosed the magnet with a closed surface. Understood? Okay. So now we know that the magnetic field lines are going to leave what? Are going to leave north pole. They are going to move away from what? Away from north pole, and they are going to enter at what? They are going to enter at south pole. Yes or no? Okay. So the magnetic field lines are going to leave north pole and they are going to enter at what? They are going to enter at south pole. Okay. So the field lines are going to leave north pole and they are going to enter at south pole, right? Okay. So we know that the field lines are going to leave north pole and they are going to enter at what? They are going to enter at south pole. So now what is the net magnetic flux that is leaving this closed surface here? I have considered a closed surface. So inside the closed surface I am having a magnet. So that magnet is going to have what? North pole as well as what? As well as south pole. So we know that always the field lines are going to leave from north pole and they again enter at what? Again they will enter at south pole. So they will always form what? They will always form the closed loops. Yes or no? Okay. So now in this case, what is the magnetic flux that is leaving the closed surface here? What is the net magnetic flux that is leaving the closed surface? Now if you observe, whatever the number of field lines that are leaving the surface here, the same number of field lines again entering the surface. So that means whatever the field lines, whatever the magnetic field lines that are leaving from north pole, the same magnetic field lines are again entering at what? Again entering at south pole. So that means the net magnetic flux that is leaving this closed surface is equal to what? Is equal to 0. Yes or no? Yeah. Okay. So here I can say the net magnetic flux that is leaving the closed surface is equal to what? Is equal to 0. Yes or no? Yeah. So we know how to represent the flux that is leaving any closed surface. Yes or no? Mathematically how to represent, we know that. Okay. So closed surface integral b bar dot dA bar will represent the magnetic flux that is leaving what? That is leaving the closed surface. So this is equal to what? This is equal to 0. Understood? So this is always true here. This is always true. Right? Okay. So I will explain why and all these things I will explain. Right? Okay. Now see here, now if I apply for this one, if I apply divergence theorem here, for this one, if I apply divergence theorem, okay, so for this LHS side, if I apply divergence theorem, so then I can write this as what here? I can write this as a triple integral. Yes or no? So closed surface integral can be converted into what? Volume integral. So by applying divergence theorem, I am going to get this as what? Triple integral divergence of b bar into what? Into dv is equal to what? Is equal to 0. Okay, so from here this volume cannot be equal to 0. So that means what must be 0 here? Divergence of b bar must be equal to what? Must be equal to 0. Must be equal to 0. Understood? Okay, so this is called as point form of point form or a differential form, point form or a differential form of Gauss law for B field, okay, and this expression is called as what? Is called as a integral form, is called as integral form of Gauss law for B field, integral form of Gauss law for B field. Understood? Okay, so this is the integral form of Gauss law for B field, and this is the point form or differential form of Gauss law for B field. Understood? Okay. Okay, yeah. Now see here. Why we are getting this result? That's what we are going to analyze here. See here. If suppose in electrostatics we have studied that if you are having a charge q, and if the charge q is enclosed by closed surface, then the flux that is leaving this closed surface here, the flux that is leaving this closed surface is equal to what? Is equal to charge enclosed by that closed surface. So that means the closed surface integral d bar dot dA bar is equal to what? Is equal to charge enclosed by that closed surface. Yes or no? Okay. Now here all the field lines are leaving what? Are leaving the closed surface, and hence you are having what? Net magnetic flux that is leaving the closed surface. Now if I consider minus q here, then what will happen here? All the field lines are going to enter what? Are going to move towards what? Towards the charge. All the field lines will move or converge towards what? Towards the charge. So in this case, what is the electric flux that is leaving the closed surface here? Is equal to what? Is equal to minus q. Right. Now if you are having both plus q as well as what? Minus q. Now if I enclose plus q and minus q with a closed surface here, then in this case, what is the magnetic flux? What is the electric flux? What is the electric flux that is leaving this closed surface here? Is equal to what? Here you are having plus q minus q. So the electric flux that is leaving closed surface is equal to what? Charge enclosed by this closed surface. So what is the charge enclosed by this closed surface? Plus q minus q. That is equal to what? That is equal to 0. Understood? Okay. Okay, yeah. So now see here. So in magnetostatics case, let us assume you are having only north pole here. Let us assume you are having only north pole. Let us assume you are having only monopole. So that is only north pole. Okay, so then what will happen here? This is just an assumption here, right? So I am assuming that only north pole is existing, let us assume. So if only north pole is existing, then what will happen? We know that the field lines are always leave what? Leave from north pole. So that means in this case the field lines must leave what? Must leave the north pole, right? Okay, so the field lines must leave, the field lines are going to leave the north pole. So now in this case, if I enclose this north pole with what? With some closed surface, then in this case you are going to have what? You are going to have magnetic flux that is leaving the closed surface is not equal to what? Is not equal to 0. Understood? Now this north pole is similar to what here? Is similar to positive charge or not? Yes or no? From positive charge, all the field lines are leaving from the positive charge. Here from north pole, all the field lines are leaving from the north pole. So I can treat this, I can call this as a plus QM here. I can call this as plus QM. This north pole, I am calling it as a magnetic charge. So that I am representing with plus QM. Why I am representing with plus QM here? Because all the field lines are leaving what? Are leaving from the north pole. It is similar to what? It is similar to positive charge in electrostatics. Understood? So this north pole, identically I am representing it as what here? Plus QM. Okay, so in this case the magnetic flux that is leaving this closed surface is equal to what? Is equal to charge enclosed, magnetic charge enclosed by this closed surface. Here the magnetic charge I am representing with what? Plus QM. Understood? Okay, now if suppose, if I consider, let us assume only south pole is existing. Let us assume here, these are all just assumptions, right? Okay, so finally we will come to the conclusion, right? So let us assume only south pole is existing. So then what will happen here? We know that all the field lines are going to move towards what? Towards the south pole. So all the field lines are going to move towards what? Towards the south pole. Now in this case, if I enclose this with what? I am enclosing this with closed surface here. So this is nothing but closed surface. Right? Okay. So now here all the field lines are moving or converging towards what? Towards the south pole. So here it is similar to what? It is similar to minus Q charge. Yes or no? So for minus Q charge in electrostatics, all the field lines are moving or converging towards what? Towards minus Q. Okay, so I am naming this here. I am naming this as a minus QM. I am naming this south pole as what here? Minus QM. Understood? Okay, so I am considering south pole as what here? Is identical to minus QM, that is a negative magnetic charge. So that's how I am considering. Okay, now in this case what will happen here? The magnetic flux that is leaving this closed surface, it will be equal to what? Will be equal to minus QM. Right? Okay, yeah. Okay. And here you will get a medium parameter also here, that is mu. Okay, so mu times of what? Mu times of plus QM or mu times of minus QM. Okay. Right? Okay. See, if I represent in terms of electric field, that is a closed surface integral E bar dot dA bar, then you can write it as what? Q by epsilon. Right? Okay, so here whenever you are representing in terms of a B field, you have to represent what? It is going to depend upon medium parameter mu. Okay, this magnetic flux is going to depend upon medium parameter mu. So if you represent in terms of H bar here, so that means B bar is equal to what? B bar is equal to mu into H bar. If you represent in terms of mu into H bar, then you are going to get what? Closed surface integral H bar dot dA bar is equal to what? In this case you can write plus QM. Understood? Okay. Okay, yeah. So if I represent in terms of H bar dot dA bar, so in this case I can write simply this as minus QM. Right? Okay, yeah. Now So if suppose, that means if you are having only north pole separately, then the magnetic flux that is leaving the closed surface is not equal to what? Is not equal to 0. If you are having, suppose if you are having only south pole separately, then the net magnetic flux that is leaving the closed surface is also not equal to 0. Yes or no? Okay, but in general, we are going to have what? If you consider a magnet, it is going to have what? It is going to have always dipole will exist or not. That means north pole and south pole will exist together. You cannot separate north pole and you cannot separate south pole. So that means you cannot have plus QM separately, you cannot have minus QM separately. They will always exist as what here? They will always exist as dipole. Yes or no? If we are having any magnetic monopoles, or if you are having free magnetic charges like plus QM and minus QM, in that case the magnetic flux that is leaving the closed surface would have been not equal to 0. Understood? Okay, but in general we don't have that situation. In general we are not having that situation. So up till now we have not discovered any magnetic monopoles here. So if you are able to discover any magnetic monopole, then you will be awarded with Nobel Prize. Okay, why? Means the total subject is going to change, right? Okay, so up till now we have not discovered a magnetic monopoles. Understood? Okay, so if you consider a magnet, okay, so it is going to have what? Always it is going to have north pole as well as what? As well as south pole. So whatever the smaller pieces you can cut, still that smaller piece is going to have what? Both north pole as well as what? As well as south pole. So that means the magnet will always exist as what here? The magnet always will exist as a dipole. Magnetic monopoles are not present. Not present means we have not discovered it. Okay, we don't know whether they are present or not. Okay, so as of now we have not discovered any magnetic monopoles, right? Okay, so that's why so if both magnetic north pole and south pole, if both are existing, then what will happen? If you are having both north pole as well as what? As well as south pole, so this is equivalent to what? You are having plus QM as well as what? As well as minus QM. In this case, if you enclose this with closed surface, in this case what you are going to get? Closed surface integral b bar dot dA bar will be equal to what? Will be equal to mu times of plus QM minus QM, that is equal to what? That is equal to 0. Okay, so that will be equal to 0. So why we are getting the magnetic flux leaving any closed surface? The magnetic flux that is leaving any closed surface, why we are getting equal to 0? Because magnetic monopoles doesn't exist, or I can say magnetic charges cannot exist freely. So that means plus QM, we are not having plus QM freely and we are not having minus QM freely. Okay, so both will exist always together. So free magnetic charges does not exist, or I can say magnetic monopoles does not exist. So that's why we are getting this result. That's why this result we are getting. So always here, always, until we will discover magnetic monopoles, always this magnetic flux that is leaving the closed surface will be always equal to what? Will be always equal to 0. So if it is always equal to 0 means from here only, by applying divergence theorem, we got the point form or differential form of Gauss law for magnetic field. So that is divergence of B bar is equal to 0. So these two results here, why we are getting these two results here? Because magnetic monopoles doesn't exist, or magnetic charges doesn't exist freely. Okay, so that's why we are getting this result. Understood? So in examinations they may ask you which of the following equations will represent that magnetic monopoles doesn't exist, or magnetic charges doesn't exist freely. Understood? So if they ask that question, then you have to, the answer is nothing but what? The answer is nothing but these expressions. Understood? Okay, so these expressions, why we are getting this result? Because magnetic monopoles doesn't exist. Magnetic monopoles doesn't exist. Understood? Okay, okay, yeah. So so write down a note here, write down a note. So if you find out any magnetic monopoles, then you will be awarded with Nobel Prize here, definitely, right? Okay, so you are going to get a breakthrough in EMT like Maxwell, right? Okay, so note so closed surface integral b bar dot dA bar is equal to 0, and divergence of B bar is equal to what? Is equal to 0. So this equations represents what? Represents that magnetic monopoles doesn't exist. Magnetic monopoles doesn't exist. Okay, or you can say free magnetic charges doesn't exist. That means plus QM and minus QM doesn't exist separately. They will always exist what? They will always exist together. Understood? Okay. So this question has asked many number of times in different types of competitive exams here. In GATE already they have asked this question. In ES also they have asked this question, and in some other PSUs also they have asked this question. Okay. Very, very simple and straightforward question. Right? Okay. Magnetic monopoles. Okay, so magnetic monopoles doesn't exist, or free magnetic charges doesn't exist. So this equations represents these things here, right? Okay. So this we call it as a Gauss law for what? Gauss law for B field. So this we call it as Gauss law for B field. Understood? Okay. So here just we have assumed here we have just assumed if at all we are having only magnetic monopole, then what will happen? If at all we are having only south pole, then what will happen? Okay. So just we have assumed here. So these are all just assumptions here. These are all just assumptions. Okay, so the magnetic flux leaving any closed surface would not be equal to 0 if you are having only north pole separately and south pole separately. Understood? Okay, but up till now we have not discovered any magnetic monopoles. Research is going on here. Research is going on, right? Okay, so if you would have discovered, then you will be awarded with Nobel Prize, and you can change the total subject EMT, right? Okay. Okay. So this is assumption here. This is assumption. So this is assumption, right? Okay. Right? Okay. So don't take it as granted here. These are assumptions, right? Okay. So if at all there exists, what will happen? That's what we have assumed. That's it, right? Okay. 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 So so if we compare in electrostatics, what are the laws that we have covered, and here in magnetostatics, what are the laws that we have covered? Okay, see here in electrostatics we have covered Gauss law for electric field. That is closed surface integral E bar dot dA bar is equal to what? Is equal to triple integral rho v dv divided by what? Divided by epsilon. So its point form or differential form is nothing but divergence of E bar is equal to what? Is equal to rho v by epsilon. So here we have determined divergence of electric field, and also we have determined what is the electric flux that is leaving any closed surface, that is equal to charge enclosed by the closed surface divided by epsilon, right? Okay, so we have deal with the flux as well as we have deal with the divergence. Understood? And also we have seen that while learning about potential here, while dealing with the potential, there we have seen that the circulation of electric field around any closed loop is equal to what? Is equal to 0. So there I have told that electric field is what? Electric field is conservative field. And how we have represented electric field here? So electric field can be represented as what here? Can be represented as E is equal to what? Minus gradient of V. So any conservative field can be represented as gradient of some scalar field. So all these things we have seen here, right? Okay. So since E bar is equal to minus gradient of V bar, E bar is equal to minus gradient of V, so we will get what? Closed loop line integral E bar dot dl bar is equal to what? Is equal to 0. Why we are getting this result here? Because the electric field is what? The electric field is conservative. Understood? Okay. Okay, here. See, E bar, we can represent it as what here? F bar by what? F bar by Q. So, F bar dot DL bar will represent what? Will represent the work done in a conservative field. So, F bar dot DL bar will represent work done in a conservative field divided by what? Divided by Q will represent the work done in a conservative field per unit charge, per unit charge. So, this closed loop line integral will represent what? Will represent, see, if I represent the same equation in this manner, okay, so F bar by Q dot what? Dot DL bar, right? So what this represents here? Closed loop line integral F bar dot DL bar will represent what? Work done in a conservative field around any closed path. By Q means what here? Per unit charge. So that means this represents what? This represents the work done in a conservative field around any closed path per unit charge. Per unit charge is always equal to what? Is always equal to 0. Is always equal to 0. So this is what we have studied here. This is what we have studied already. Right? Okay. Himanshu Sharma, I have some doubt. What is V here? Which one here? Which V? Here, V is a potential here, V is a scalar potential. I have taught this already earlier. In the earlier classes, I have taught about this is circulation of electric field and the relation, how we are getting this relation equal to minus gradient of V. V is nothing but what? Scalar potential, right? Okay. So all these things I have already taught here, right? So in the previous sessions it is present, right? If you want to know about this electrostatic potential and this electrostatic field, so then you have to go through the previous lectures, right? Okay. So we are having good number of lectures on this electrostatic potential, energy, electrostatic potential, and all these things, right? Okay. So please go through that EMT playlist here, EMT playlist. Okay, in GATE Academy Global channel, go through EMT playlist. Okay, so there we have covered all these things here. We have covered all these things, right? Okay, yeah. Okay. See, we have studied here, we have already studied all these things here, just I am revising here, that's it. Okay. Okay. So if you apply Stokes theorem for this one, then what we got here? What we got? We got curl of E bar is equal to what? Curl of E bar is equal to 0. Okay. So these are the results we got in case of what? In case of electrostatics. In case of electrostatics, right? Okay. So in case of electrostatics, so these are nothing but what? This is nothing but Gauss law for electric field, yes or no? This is nothing but Gauss law for E field. This is nothing but Gauss law for E field, right? Okay. So we have determined the divergence of electric field as well as we have determined what is the circulation of electric field. What is the circulation of electric field about a given point, or I can say simply curl of electric field is equal to what? Is equal to 0, and E bar is equal to what? E bar is equal to minus gradient of V. Okay. Okay, here. So all these relations we have studied here. Already we have studied all these things. See, the units of electric field, is volt per meter, and the units of DL bar is nothing but meter. So here meter will get cancelled. So it represents what here? It represents a summation of voltages around any closed loop is equal to what? Is equal to 0. There I have told that this equation is the basis for what? Is the basis for KVL. So this equation is also called as what? Is also called as KVL. Okay. So all these things we have covered here, right? Okay. Okay. Now in magnetostatics here, right? So so in magnetostatics we have seen the magnetic flux that is leaving any closed surface is always equal to what? Is always equal to 0, and divergence of B bar is equal to what? Is equal to 0. And we have seen that from Ampere's law, we have seen that circulation of B field around any closed loop is equal to what? Is equal to mu times of what? Mu times of I enclosed. We have represented the same expression in terms of what? In terms of Z bar also. So what we got here in terms of Z bar? In terms of Z bar, how you can represent? Mu into what? Mu into double integral Z bar dot what? Z bar dot dA bar. Z bar dot dA bar. Right? Okay. Sorry. Okay. Okay. So this is the integral form of Ampere's law. Yes or no? This is the integral form of Ampere's law we got. Now if you apply Stokes theorem to this one, so what we got here? We got curl of B bar is equal to what? Is equal to mu times of what? Mu times of, sorry, what we got here? Mu times of what? Mu times of Z bar. Mu times of Z bar. So the same thing I can represent. If you substitute B bar is equal to mu into H bar, here mu will get cancelled. Therefore you are going to get del cross H bar. Curl of H bar is equal to what? Is equal to Z bar. Okay. So all these expressions we have already derived here. Right? Okay. Now if you observe here, divergence of B for so these are the conclusions we have drawn here. These are the conclusions we have drawn in electrostatics and magnetostatics. Right? Okay. So now see here the divergence of electric field, is equal to what? Is equal to rho v by epsilon. Is equal to rho v by epsilon. See, if I consider charge free region, only in that case rho v will become equal to what? Rho v will become equal to 0. So if I consider a charge region, then divergence of E bar is not equal to 0. So that means here we cannot say electric field is solenoidal or non-solenoidal. We cannot say. Why here? Because here see, we know that for any vector field, if the divergence of vector field is equal to 0, then that vector field is said to be what? Then that vector field is said to be solenoidal. Yes or no? Here in electrostatics we are having this expression here, that is divergence of E bar is equal to what? Is equal to rho v by epsilon. So now here if rho v is not equal to 0, then E field is what? E field is not solenoidal. Yes or no? Then in that case the E field is not solenoidal. Right? Okay. Now if I consider rho v is equal to 0, for this expression I am talking here, right? Okay. So if I consider rho v is equal to 0, then divergence of E bar is equal to what? Divergence of E bar is equal to 0. In this case I can say the electric field is what? In this case I can say the electric field is solenoidal. So that means the electrostatic field may be solenoidal or may not be solenoidal. It depends upon what? It depends upon the charge. It depends upon the charge density rho v. So if rho v equal to 0, then we can consider the electric field as what? Solenoidal. So if rho v is not equal to 0, then electric field is not what? Is not solenoidal. So that means we cannot guarantee that electric field is what? Electric field is solenoidal or non-solenoidal. We cannot guarantee that. It all depends upon what? It all depends upon rho v. Understood? If you are considering a charged region, understood, then in that case rho v is not equal to 0. In that case electric field is not solenoidal. If you consider charge free region, then in that case divergence of E bar is equal to 0, then you can say electric field is solenoidal. But here you cannot guarantee that whether electric field is solenoidal or non-solenoidal. We cannot guarantee that. It all depends upon rho v value. Understood? Okay. So that's what you have to understand. So next, if you consider curl of E bar is equal to what? Is equal to 0. Curl of E bar is equal to 0. And here E bar is equal to what? E bar is equal to minus gradient of V. Understood? So curl of E bar is equal to 0 is always true here. Is always true. Yes or no here? Is always true. Why here? We know that E bar is equal to what? Minus gradient of V. So that means curl of in place of E bar, if I substitute minus gradient of V. So from null identities, we know that curl of gradient is always equal to what? Is always equal to 0. Is always equal to 0. So that means curl of E bar is equal to 0 is always true. So that means this electrostatic field is always what? Is always conservative. Is always conservative. Understood? Okay. So electrostatic field is always what? Is always conservative. How we are saying here? Because we know that curl of any vector field, if curl of any vector field is equal to 0, then that vector field is said to be what? Is said to be conservative or curl free or irrotational. Understood? So in electrostatics, always curl of E bar is equal to 0 and E bar is equal to what? E bar is equal to minus gradient of V. So curl of gradient of V will be always equal to what? Will be always equal to 0. And hence we can say E bar is what? E bar is always what? Always conservative. Always conservative. So electrostatic field here. Electrostatic field. So what is the conclusion we can make here? What is the conclusion we can make? Electrostatic field. Electrostatic field is always what? Is always conservative. Is always conservative. But we cannot guarantee. About what? About solenoidal. Okay. So it may be solenoidal or it may not be solenoidal depending upon rho v. Understood? Okay. But what we can guarantee here? Electrostatic field is always what? Is always conservative. Is always conservative. Right? Okay. This is the conclusion we can make. Now coming to magnetostatics here. So these are the expressions we got. Right? Okay. So now here what we are having here? Divergence of B bar is equal to 0. So if divergence of any vector field is equal to 0, then that vector field is said to be what? That vector field is said to be solenoidal. That vector field is said to be solenoidal. Yes or no? So divergence of B bar is equal to 0 is always true. Yes or no? Is always true. Right? So why it is always true here? Because we have not discovered yet any magnetic monopoles. Understood? Okay. So always this magnet will exist as what here? Will exist as dipole. Magnetic monopoles doesn't exist, and hence always divergence of B bar will be equal to what? Will be equal to 0. So this implies what? This implies B bar is what? B bar is always what? B bar is always solenoidal. B bar is always what here? B bar is always solenoidal. Is always solenoidal. Okay. Okay. Yeah. Next, if you consider curl here, so curl of B bar is equal to what? Is equal to mu into Z bar. So that means if current density is not equal to 0. Okay. So here if Z, or I can write simply current density. If Z not equal to 0 here, if Z not equal to 0, then curl of B bar is not equal to what? Is not equal to 0. If Z is not equal to 0, then curl of B bar is not equal to 0. Right? Okay. Next, if Z equal to 0, then only curl of B bar will be equal to what? Curl of B bar will be equal to 0. Okay. So that means here so that means if current density is not equal to 0, then curl of B bar is not equal to 0. If current density is equal to 0, then curl of B bar is equal to 0. So that means here the conservativeness, that means whether the B field is conservative or not, it depends upon what? It depends upon the current density. If suppose they have given current density is not equal to 0, then in that case B field is not conservative. If the current density is equal to 0, then in that case B field will become what? B field will become conservative. Understood? Okay. So that means you cannot guarantee that B field is what? B field is conservative or non-conservative. Understood? Okay, so it all depends upon what here? It all depends upon the current density. So if you are having the current density, if current density Z is not equal to 0, then B field is non-conservative. If the current density Z equal to 0, then B field is what? B field will be conservative. Understood? Okay, so in this case we can say B field is what? B field is non-conservative. B field is non-conservative. Okay, so in this case B field is what? In this case B field is conservative. So that means we cannot guarantee the field is conservative or non-conservative. So it depends only on what? It depends only on current density. It depends on current density. Understood? Okay. See, if suppose they have not mentioned anything about the current density, then you should not take it as equal to 0. You should not take it as equal to 0 unless they will specify. Okay. So if they have not mentioned anything about the current density, then you should not assume the current density is equal to 0. Understood? Then in that case, we will assume current density is not equal to 0. Then in that case, we will simply say B field is what? B field is non-conservative. If they are not talking about Z bar, if they have not talked about Z bar, then we should not assume Z bar is equal to 0. Understood? Okay, so in that case we have to assume Z is not equal to 0. So in that case B field will be what? Will be non-conservative. B field will be non-conservative. So in general, if they have not mentioned anything about the current density, if simply they are asking about the B field, then you simply say B field is what? B field is non-conservative. If specifically if they mention if the current density is equal to 0, so then only you have to tell B field is what? Conservative. Understood? But what we can guarantee here? What we can guarantee? B field is always what? B field is always solenoidal. B field is always solenoidal. Understood? Okay. So here the electrostatic field is always what? Is always conservative. Right? Here you cannot guarantee the solenoidal of electric field, and here you cannot guarantee the conservativeness of the B field. It depends upon the current density here. Here it depends upon the charge density. Understood? Okay, so these are the observations we can make here. These are the observations we can make. Okay, right? Right? Okay. Okay. So we have defined divergence of electric field and curl of electric field. And in magnetostatics, we have defined divergence of magnetic field and also curl of magnetic field. Understood? Okay. So all these things we have seen here. Right? Okay. Right. So these points are very, very important here. These points are very, very important. So they are going to ask you the questions directly. Right? They are going to ask you the questions directly. So these statements will come directly in the exam here. Right? Okay. Okay. Right. Okay. So with this we have completed electrostatics part and magnetostatics part. With this we have completed electrostatics part and magnetostatics part. Okay. So next we will start with time varying fields here. Next we will start with time varying fields. That means from now onwards the fields are going to vary what? Are going to vary with respect to what? With respect to time. With respect to time. Right? Okay. Okay. So up till now we have dealt with electrostatics and magnetostatics. So next we will start with time varying fields. So in this time varying fields we will cover Faraday's law here. First we will cover Faraday's law. Right? Okay. So next topic we will cover modified Ampere's law here. We will cover modified Ampere's law. Okay. Right. So these two are very important laws here, which leads to the discovery of what? Discovery of electromagnetic waves. So we will see all those things here. We will see all those things, right? Okay. So just I will give you So now the time is 5:30 already. Okay, so what I will do here is we will start Faraday's law tomorrow here. Okay, we will start Faraday's law tomorrow. Why means now the time is already 5:30, right? Okay, so it will take at least 1 hour, minimum 1 hour time to explain just the basic of Faraday's law. Understood? Okay, so we cannot stop it in between, right? So that's why I'm going to start this Faraday's law from tomorrow onwards, right? So we'll deal with time varying fields from tomorrow onwards. So we'll start Faraday's law tomorrow here. Okay, so with this I'm winding up the session. So tomorrow exactly at 4 p.m. Tomorrow exactly at 4 p.m. we are going to start the session, and tomorrow we'll start what? We'll start freshly with time varying fields, that is Faraday's law. First we'll start with Faraday's law, right? Okay. Okay, so tomorrow exactly at 4 p.m. we will meet and we will start Faraday's law. Okay, so until then, take care. Bye bye.